Hi, I'm Brendan, a postdoctoral researcher at IIT Bombay. In this talk, I'm going to present my recent research work on black box identity testing of non-commutative rational formulas of inversion and truth. It is joint work with V. Irving and Parthenworth. If you're not familiar with the terms, don't worry. In this talk, we are going to define the terms. So this talk is about rational identity testing, briefly RIT. So before we define what is this RIT problem, let us first go over what we mean by polynomial identity testing. So what are polynomial identities? From our school days, we have seen a lot of polynomial identities, like the first two well-known identities, or like the last two not so well-known identities. So why do you call them identities? Because on the left-hand side and on the right-hand side, they are computing the same polynomial. What do you mean by they are computing the same polynomial? In the syntactic sense, if you think of them as formal polynomial, if you write them as like term by term, then the coefficient associated with every term is same for both the polynomials. Whereas in the semantic sense, we can think of it as like if you evaluate the polynomials on some inputs, then they will output the same value. Okay. So equivalently, you can think of instead of two polynomials, only the one polynomial, whether it is computing the zero polynomial or not. Okay. So how do we test that? So from the syntactic definition, it gives us an immediate algorithm that we can write it as like we can expand it term by term, and we can check the associated coefficient, whether it is zero or not. Like say for univariate polynomial of degree d, we can think of it as d plus one dimensional coefficient vector, and we can check whether this is a zero vector or not. But the problem is that, like, if you have an invariant polynomial of degree d, then the number of terms can be as large as like n plus d choose d. So it is important how the polynomial is given to us. How is it represented? If the polynomial is given to us as like a list of coefficients, then polynomial identity testing is easy. We can just scan the coefficient vector and we can do this in type polynomial to the input side. But in this case, we use an arithmetic circuit, which is a succinct representation of this multivariate polynomial. So what is this arithmetic circuit? If you are familiar with Boolean circuits, you can think of it as like an algebraic analog of Boolean circuits. So in Boolean circuits, we have some input nodes labeled by some variables, and the internal nodes are labeled by OR gates and gates, and there is a designated output node which is computing the Boolean function. Just like that, in arithmetic circuit, we have these input nodes labeled by some variables, and the internal nodes are labeled by some basic arithmetic operations like additions and multiplications. And then in the output node, we are computing a multivariate polynomial over these input variables. If we put a structural restriction on this directed acyclic graph that the fan out of the internal nodes are bounded by 1, then the DAG will have a tree structure and we call it an arithmetic formula. Okay, so now we can formally define the polynomial identity testing or PIT problem, that given such a polynomial by an arithmetic circuit or an arithmetic formula, test whether it is computing a zero polynomial or not. And ideally, we want to do this in polynomial time, polynomial in the size of the circuit. So there are two types of polynomial identity testing problems. One is white box problem, where we can see how the polynomial is being computed by the circuit. We can probably get some extra advantage from that. The second one is the black box identity testing, where the polynomial is given to us by an evaluation oracle. And to test identity, we'll use the semantic definition that if it is non-zero, then there will exist some evaluation where it will be non-zero. Okay, so what is this black box PIT problem? The idea is that for a given class of polynomials, we want to find a list of evaluations such that for every non-zero polynomial, if it is non-zero, then we'll find a point in the list, we'll find an evaluation in the list such that it will give us a non-zero value. we'll call this non-zero evaluation a witness. So a witness of every non-zero polynomial in that class will be able to find in that small list of evaluations. Okay. So to get some intuition, consider this simple example. You have say class of infinite polynomials of degree t. And suppose the list of evaluations we have, that is just like some d plus 1 many points. So we have a list of length d plus 1. And what do we know? If one univariate polynomial is non-zero, it is of degree d, it can have at most d many roots. So if it is non-zero, we can find a witness of its non-zeroness in that list of d plus 1 many points. Okay, so this list of evaluations, it is formally called a Hitting set. So we define a Hitting set with respect to a circuit class. So suppose we have a Hitting set H against a circuit class C. What does it mean? That consider any non-zero polynomial in that circuit class C. By non-zero, we know that there is a witness, that there is some evaluation where it will be evaluated to a non-zero value. And you'll be able to find that witness in that list of evaluations that you are given. If it is non-zero, then there will exist a witness in that small list. So just like invariant polynomial has a Hitting set of d plus 1, you can show that invariant polynomial of degree d has a Hitting set of size d plus 1 power n. Now, this is the best Hitting set size that we know. We can get a randomized polynomial time algorithm by querying a polynomial in the grid of size d plus 1 power n. From the polynomial identity lemma, we know that if we are given a non-zero polynomial, then with high probability will be evaluating to some non-zero value. Okay. Now, de-randomizing this PIT is an interesting open problem that is open. Okay. So still now, whatever we have discussed, we allowed in arithmetic circuit, we allow basic operations like addition and multiplication. Now, suppose we are also allowing inverse get in our arithmetic circuit. Clearly, it will not compute a polynomial anymore, it will compute a rational function in the function field. But what do we know that any element of the function field, any rational function, can be represented as like a ratio of two commutative polynomials f and g. So what Strassen showed that if you are given such an arithmetic circuit with inverse gates, you can push the inverse gates to the top of the circuit. You can think of there is only one inverse gate in your circuit, and that is at the top of the circuit. And so if you are given a rational function and if you want to check whether it is computing 0 in the function field or not, you can just reduce it to commutative PIT, as you know that it will be a form like f by g, and you will do PIT for f and g. Okay. So now we'll study one more restricted model of arithmetic computation, which is called non-commutative computation. So when we are computing these polynomials, we didn't differentiate between monomials like x1, x2, and x2, x1. We think of them as like same terms. But now think of them as like strings. So we'll consider them as two different strings. In other words, you can think of it like, suppose in arithmetic circuits, the multiplication gates respect the order of their inputs. So the left child into the right child is not same as the right child into left child. In that case, it computes a non-commutative polynomial that you can think of as like some finite linear combination of the strings that sits inside the free algebra. And this non-commutative PID problem is to decide if you are given such a non-commutative arithmetic circuit, computing whether it is decide whether it is computing a zero polynomial in the free algebra. To see how different is it from the commutative setting, just consider the example that we had already seen. X1 plus x2 into x1 minus x2 equal to x1 square minus x2 square. It is true in commutative setting, but it is no more an identity in the non-commutative setting. As x1, x2, and x2, x1, they are not going to cancel each other. So in black box PIT, as we have seen that whenever our polynomial is non-zero, whenever it is not an identity, we have found a weakness that tells us that okay, if you evaluate it on it, you will get some non-zero value. So, what is the corresponding evaluation in case of non-commutative setting? So, in non-commutative setting, the idea is to come up with matrix evaluations, and similarly, the heating set definition is like for a given class of non-commutative circuits, non-commutative polynomials, we are the idea is to output a list of matrix tuples, list of matrix evolutions, such that for every non-commutative polynomial, whenever we know that it is non-zero non-commutative polynomial, we know that there is some matrix evaluation for which it is non-zero, and we'll be able to find a weakness of its non-zeroness in this list of matrix evaluations. Okay? So, unlike commutative setting, in non-commutative setting, in PIT front, it is quite well understood. I'm not going to go over all the PIT results, but the result which is important for us is that for non-commutative formula of size S, if we have a class of non-commutative formula of size S, then we have such a small list of matrix evaluations where the list is bounded by S for order log S. So we have a quasi-polynomial size heating set for such class. Okay. So now we have come to the main part of this stuff where we introduce inverse gates in a non-commutative arithmetic circuit. Formally, it computes the non-commutative rational functions in the universal phase field. Okay. So what does it mean? Suppose you are given two non-commutative rational formula and you are asking whether it is a rational identity or not. So you will say that they are computing the same rational function in the phase field if for every matrix substitution, whenever they are defined. First, notice that they may not be defined as you are introducing inverse gate and you are substituting matrices. So it may happen that you are trying to take the inverse of a matrix which is not even invertible. So it may not be defined. If on an evaluation, if both sides are defined, then they must agree. So that was the definition. It was characterized by Anisu as the definition of universal phase field. Then we say that they are computing the same rational function in the phase field. So this object behaves peculiarly in the sense that they don't have any canonical representation. Unlike non-commutative polynomials or commutative polynomials or even commutative rational functions, we don't have any canonical representation for this object. And the rational identity testing problem is that given such a non-commutative rational formula, decide whether it is computing the zero function in the phase field. Or equivalently, you can think of it like this, that given such a non-commutative rational formula, does there exist a matrix evaluation of any dimension, a matrix evaluation, such that if we evaluate the formula on this matrices, it will give us a non-zero value. Okay. So, how non-trivial it is, just take this simple example, this identity, which is famously known as Bose identity. How to prove that it is zero in the phase field? As we don't have any canonical representation, it is not immediate how to get an algorithm. So, this problem is quite well studied in recent years. And what we know about this problem, that in white box, if we can see how the formula is computed, given this non-commutative rational formula, over rationals, we can get a deterministic polynomial time algorithm because of Gerd, Goodwitz, Oliver, and Witter-Sussberg. And then even as and Subramaniam extended this to over finite fields also. Whereas if the formula is given in black box, then we have a randomized polynomial time algorithm for this problem. But the open problem is to de-randomize this black box variety. Or equivalently, you can think of that we want to get a heating set for rational formulas. That if we are given a class of rational formulas, we want to output a small list of matrix evolutions so that if we have a non-zero rational formula, we'll be able to find a witness of it. Okay. So before we go to our result, just notice one thing, that in commutative setting we had seen like we could push all the inverse gates to the top. So it doesn't matter how many inverse gates are there. It doesn't even matter how many nested inverses are there in any leaf to root top. But in non-commutative setting, it matters. And it is characterized by the inversion height of the rational formula. So what is inversion height? You take a formula, you look at leaf to root path and leaf to root path, and what is the number of nested inverses. And you take the maximum of such nested inverses. So Rubis and Peterson, they showed that if you take Sige's formula, then the number of such nested inverses, this inversion height, is bounded by log of S. Okay. Now this black box RIT problem, it is even open when the inversion height is only 2. We didn't have any idea how to deal with the nested inverses. Okay. So what is our result? We show a quasi-polynomial such heating set for the class of non-commutative rational formulas of inversion height 2. Let us go over the statement carefully. So suppose we are given a class of non-commutative rational formulas of Sige's of inversion height 2. What does it mean? Take any formula, take a tree structure where the nodes are labeled by the addition, multiplication, and inverses, and it is promised that you are not using more than as many basic operations, additions, multiplications, and inverses. And it is also promised that in any leaf to root path, you will not see more than 2 inverses. For such class, we can output a list of matrix evaluations such that if a non-commutative formula is non-zero, that is, if there is some matrix evaluation of some dimension in the universe, then the list that we are providing will be able to find a witness of its non-zeroness in that quasi-polynomial site list of matrix evaluations. Okay. So I think I have around 10 minutes. Okay. So for the remaining time, I will try to go over the proof idea that we have. Okay. So first observe one thing. Suppose a rational formula, we know that it is defined on some matrix tuple, say P1 to Pn. Then suppose it is of inversion at H, okay? Then every subformula of phi H minus 1, say R1, R2, R3, R4 in this figure, they must be invertible on that point P1 to Pn. Otherwise, R of P1 to Pn would not have been defined. Okay. And what we observe that if a rational formula is given to us with the matrix tuple P1 to Pn such that R is defined at P1 to Pn, then we can do rational identity testing. We can construct a heating set for R efficiently. To show that, we use ideas from this paper of Volchich, Matrix Coefficient Realization 3, a nice paper of Volchich, where he introduces this notion of generalized automata. So I'm not going to define this notion. So intuitively, what we do, that we shape the rational formula by this point P1 to Pn. You can think of it as like some non-commutative analog of Taylor series expansion, and then we can construct a heating set efficiently. So if we want to do this, the thing is that for the smaller inversion height, we need to ensure that they are invertible, not only non-zero. That motivates us to define this notion of strong heating set. In heating set definition, we just ensured that this R of P1 to Pn would be non-zero. Now we are saying that in the list of evaluations, there will be one point such that R of P1 to Pn will also be invertible. So you may ask, how do you know that whether such strong heating set exists or not? So the existence follows from the work of Yunus and Subramanian. So for our case, where our goal was to design a heating set for inversion 2, now the refined goal is to design a strong heating set for height 1, for rational formulas of height 1. Then we can just shift it and we can design this heating set of height 2. Okay. Now, how to construct this strong heating set of height 1? The previous approach fails in the sense that if we just take some arbitrary matrix tuple where the formula is defined, and if we just shift it, for the shifted formula, we can find a heating set that will only ensure that it is non-zero, but it can't ensure that it is invertible. So the idea was that if we put some more structures, some more restriction on the point where it is defined, probably that can be helpful. And the structure that we impose is that, suppose in this P1 to Pn, the PIs are coming from some division algebra. So what is division algebra? Intuitively, you can think of a division algebra is like a matrix algebra only, but here you can do addition, multiplication, and also division free. What does it mean? That whenever you have a non-zero matrix, it is invertible. So you can freely take the inverse of that matrix. And we define this notion of division algebra heating set where the substitution is from a division algebra. So what happens that suppose we have a rational formula, we are substituting some elements from division algebra heating set. Whatever we are getting, we know it is non-zero and we know it is inside the division algebra. Therefore, we know that it must be invertible. So any division algebra heating set is the strong heating set. So all we now need to do to construct a strong heating set of height 1, to construct a division algebra heating set for height 0, which is just non-commutative formula. And that is exactly what we do. So overall, the idea is the following, that our goal was to come up with a heating set of height 2, and for that we saw that it suffices to come up with a strong heating set of height 1. And to get a strong heating set of height 1, we had to shift it by some division algebra elements. So we had to come up with a division algebra heating set for non-commutative formulas. And by modifying this Probst-Pilica heating set and using some ideas from cyclic division algebra, we are able to show that we can embed that Probst-Pilica heating set inside a division algebra heating set. Okay? So this is the overall idea. So now let me summarize. So the idea was to design a heating set. Then we observed that we need to do something stronger. We defined this notion of strong heating set. And that turned out not enough. So we came up with this idea of division algebra heating set. Okay. But even with that idea, we are not able to go beyond 2. So if we look at this figure, that from a division algebra heating set of height 0, when we are getting this strong heating set of height 1, we know that the entry is invertible. It is a strong heating set, but we don't know whether it is inside a division algebra or not. Okay, if we can ensure that it is inside a division algebra, then we can just continue the induction and our technique can be extended for any constant inversion rate. Okay, so let me finish by stating this open problem, that can you come up with a heating set for rational formulas of arbitrary inversion rate? Thank you.